Okay, welcome. So now we're going to do another example of work, and this is work done by pumping out a tank or some other object, but basically pumping out fluids out of, it could be a tank, it could be a tub, it could be anything. Now, it could be a pool, right? So, excuse me. I'm going to use this example of a cylinder, okay? But the amount of work done to pump out a liquid like water out of a container depends on the shape of the container, so that's one thing. It also depends on the height that it moves, right? So that makes this these pumping problems more complicated, is that it depends on those two things: the shape of the container and the amount of distance that you're lifting the fluid to get out of the tank. Okay? In this example, I'm going to start with a cylinder because a cylinder has a constant shape as the tank empties. So I start with a full tank. We don't have to start with a full tank, but if I start with a full tank all the way to the top, then I want to find out how much work does it take to empty the tank. Now, or to empty it halfway, whatever the case may be. Now, the other thing too is the way we're going to orient the tank. In this case, I'm orienting the tank so that the axes are like rotated 90 degrees clockwise, so that the y-axis goes this way and the x-axis goes down. So that way, we're measuring the amount of space, right? As the liquid goes down, the amount of empty space increases, so that by the time that the tank is empty, then we'll be at the height of the tank, right? So again, the height of the tank is going to be constant, the radius of the tank is constant, so some things are being held constant for us. Now, if I start at 0, then I'm going to end, and the amount of empty space will end up being the amount of fluid that was removed. So, what else can I say? Okay, so let's set this up. So, the way we're going to do this is we're going to partition the volume, the amount of volume that's being lifted up, as like a disk, right? Because we're going to basically think about layers of water, okay? So if we remove small layers of water, we could treat them as a disk, a thin disk of water. And so if we partition our tank vertically, and so the distance that we're going to, the amount of water that we're doing is going to be represented by these partitions, right? So we're partitioning the line. And so we're going to take a disk, a very thin disk, from x sub I minus 1 to x sub I. And we're going to take this disk. Now, again, the disk is circular, right? But it's a little tiny disk. Or we could look at it as a solid, right? A short, solid cylinder, right? So if I wanted to find the volume of that thin disk, I would use the formula for the volume of a cylinder, which would be pi r squared h, okay? Now, in this case here, excuse me, okay, r is constant, okay, so that's going to be a constant. H, the height of this disk here, this thin disk, is going to be from x sub I minus 1 to x sub I. So we're going to rewrite this as pi r squared times, well, we're taking regular intervals. So again, this distance is going to be regular, so it's going to be the same. So it's going to be x sub I minus x sub I minus 1. And so again, this is just going to be delta x. Okay, so that's the volume. Now, this is cubic units, right? So these are units cubed. Oops. Okay. Now, one other thing too, we're dealing with volume. What are we trying to calculate? We're trying to calculate work. Okay? Before we calculate work, we need force. The amount of force needed to lift a volume of water up a certain distance, right? So, but we're talking about volume now. Okay? So we need to deal with something that's going to help us get the units for force. Okay? Well, that's where weight density of water comes in. So again, a lot of these problems are going to be with water. Again, if we deal with something like oil or something, they'll give you the weight density in the problem. Okay, but water is so common that you should know these. Okay, these you should memorize. Okay, if it gives you some other fluid, like oil or something like that, that should be given to you in the problem. So the weight density of water is given by either metric or US customary. So 9,800 newtons per cubic meter of water is the water density. In US customary units, that is 62.4 pounds per square foot, or excuse me, cubic foot. So these are the water densities. Okay, now we're going to take the volume times the weight density, not the water density, I mean the weight density. The weight density, and these units will cancel to give us the force. Okay, so let's do that. So if we take force, let's do that here. Oops. Just want to make sure I'm doing this. Okay, so we use 9,800. So in this case here, the force would be represented by the density times volume, which would equal density, or in this case the weight density, pi r squared delta x. Okay, so now what about work? Okay, now we're going to have to bring in the amount of distance that's being traveled, and this is where the sample point comes in, right? So we're going to pick a sample point because, again, we're assuming a thin disk, so we're going to assume that the amount of work is pretty much the same for the thin disk. So we're going to use x sub I star as our sample point. And so what are we going to use for the distance? Well, we're going to use x sub I, right? So the distance that it's moving is x sub I. So remember, work is force through a distance. So work sub I, so the work for this thin disk, is going to be the force times distance, right? So let's put it together. Well, work sub I is going to be the density times the volume times the distance, which in this case is going to be rho, the weight density of the liquid, times pi r squared delta x times x sub I star. Okay, so if we rearrange this, right? So if we rearrange this, then what we're going to get is, again, let's pull the constants here. So this is constant. We're going to put the delta x. So this is going to be rho pi r squared times x sub I delta x. And in this case here, those are constant. So the only thing changing is the distance that it's being lifted to get out of the tank. And then of course, if we take this Riemann sum, so our work is be approximately the sum from I equals 1 to n of this formula, which is going to be rho pi r squared x sub I, delta x. And really, all of this is constant except for this, because that's the only thing that has I in it. That's the only thing that's changing. Literally, we could take all of these out and write this as the sum. Oops. Well, you know what? I'm not going to do that because it's not always the case that this is going to be constant. But these two would be constant. Okay. But let's not do that, because technically I could take these out of the sum and rewrite the sum. But let's just go with what we have. So now let's take the limit. So now what is work equal to? It's going to be the limit as I goes, as n goes to infinity of the summation as I goes from 1 to n of rho pi r squared x sub I delta x, and then that gives us what? It gives us the integral from a to b of the interval, okay? Or in this case it could be 0 to h, the height of the cylinder, right? But again, just to keep it general, of rho, which is the weight density of the fluid, pi r squared, which is the radius, okay? In this case it's constant, x dx. Okay. Okay, so in the next video, I'm going to go through the steps of doing this. And then what we're going to do is tackle an example where we don't have a constant radius. So we'll talk about cones. Okay, and well, how do we deal with a cone? In that case, the radius changes as the depth or the height changes that you're moving the water. So that's going to have to be worked into that. Okay. See you the next time. Have a great day.